Inverse variation is a relationship where the equation or the data can be modeled by either the equation y equals k over x or xy equals k, where k is the constant of variation. These are for problems where when one of the variables goes up, the other value goes down, or vice versa. For example, a real-life situation is when you're going on a road trip that is like 50 miles. If your speed or rate goes up, then the time it takes goes down. Or if the rate you're traveling at drops, the time it takes goes up. So that's a situation with inverse variation where this 50-mile distance is the constant of variation because it's not changing no matter what your actual rate is. And then the rate and the time are the two variables. And as one of them increases, the other one decreases to correspond with that. Then as we go through some of the problems here today, there are other ways of solving these for variation. I'm choosing to use an approach that works for other types of variations as well as inverse variation, to make a consistent approach. This way, if you go to something that is a combined variation of direct and inverse, for example, giving us an equation that might be like this, then you can apply the same approach to that you do here in this video for inverse variation to a situation like this. It's just a little bit more complex of an equation. In this example, we are asked to determine if the values in the table below represent inverse variation. Now, there's a couple ways we can do it, but no matter which way you choose to do it, it usually involves finding the constant of variation, and you can use one of the two versions of the formula, either y equals k over x or xy equals k. And given the context, since we're not really using it for anything else, xy equals k is probably the easier formula to use in this situation, where we can just multiply x and y and see if the value for k is the same the whole way down through. So in this first example, if I take my first x and y in the first table here, and I take 1 and multiply it by the value for y, which is 12, that will give me the value for k. In other words, 1 times 12 is 12. So I know k should be 12. So if this table is inverse variation, then that means the k is going to be the same for all of the different combinations of x's and y's. That's what it means to be the constant of variation. So if I go and check through the other ones, we have 2 and 6. So 2 times 6, is that indeed 12? Well, yes, it is. 3 times 4, just multiplying our x and y values using the xy equals k. 3 times 4 is also 12. Next one is 4 for x and 3 for y. 4 times 3 is still 12. And 6, I keep putting a comma, times 2 is also 12. And 12 times 1 is also 12. Since it was the same the whole way down through, since the constant of variation came out to be 12 the entire time, this is indeed an example of inverse variation. On the table on the right here, if I tried to do the same thing, taking my x and y value, so xy equals k using this formula, plug in x, which is 1, y, which is 20. That should give me k. So 1 times 20 is 20, which means the constant of variation, if this is indeed inverse variation, should be 20. If I continue with the next one, 2 and 17, and I multiply them, that doesn't give me 20, it gives me 34, which is not the same thing. So because even just one of them failed, this is not inverse variation. You can also use the other equation to show the same thing. No matter which table you use, if you're using the y equals k over x to do this, I'm just going to use the one on the right here. So if you're using y equals k over x instead, you would plug in x and y. So y is 20, k we're looking for, and x is 1. Multiply both sides by 1, and get 20 is k. And then to figure out the rest of the table to see if it's inverse variation, all you do is use the equation y equals 20 over x and see if this equation works for the rest of the table. So you would replace x with 2 because that's my next x value, and you would see if that is 17. So 20 divided by 2 is not 17. Therefore, this is not inverse variation. So you can still use y equals k over x to do the same thing and show whether it's inverse variation or not just by using the other formula. Okay, this example starts off with in an inverse variation, x is 10 and y is 3. We're going to write the equation to represent the inverse variation and then find the value of y when x is negative 6. Oftentimes with inverse variation problems, there are 3 different phases a problem might go through. The first phase is to find the value for k. The second phase is to just write the equation. And the third phase is to use the equation to find a value. In some cases, you might only be looking for k. In some cases, you might only be looking for the equation. In some cases, you're asked to do all 3. But you always start by finding the value for k and then work your way through. So in order to do phase 1, we need to figure out what type of variation and setup it is. This topic is only using inverse variation, so that's our focus here. It does say inverse variation, and since we are doing inverse variation, we can use either y equals k over x or xy equals k. It doesn't matter which version you use. So I'm just going to use xy equals k here. So xy equals k. So to find k, you have a piece of information that goes together. By goes together, it means you have both the x and y that correspond to each other. That is this part of the problem right here. The x is 10 when y is 3. Those two values go together. So I'm going to replace x with 10 and y with 3, allowing me to figure out what k is, and we have k is 30. So the constant of variation is 30. Now on to phase 2 to write the equation. So when I write the equation is just when we replace k with whatever the constant of variation is. It's the situation or expression that can be used repeatedly with different values and all corresponding to the same original inverse variation data. And then for the third phase, we actually go and use that equation. So now that we have xy equals k, we just use our third set of information, or our last piece of the problem here. We are looking for the value of y when x is negative 6. So in my equation, I'm going to replace x with negative 6. We don't know the y value that goes with it, so y is just y. And now that we already know what k is, k will always be the same for this situation. Now we just have to solve the equation for y, so we'll divide by negative 6 on both sides and get y is equal to negative 5. Okay, in this example, the weight needed to balance a lever varies inversely with the distance from the fulcrum to the weight. Where should Willis, who weighs 150 pounds, sit to balance the lever with Frankie, who weighs 120 pounds and is sitting 6 feet from the fulcrum? So first off, this is a word problem or an application problem here. So just to emphasize the point of this is essentially a seesaw. The fulcrum is right here in the middle. And the distance that's referring to is the distance from the center to either side. Since we're not regarding direction here, so it's just a positive distance. Okay, so we're going to use the same approach we did before, 3 different phases. First phase is to figure out the constant of variation. Now this is a word problem, however, so I like to use letters that actually make sense in the situation. And if you follow through how it's read, you can easily figure out the setup. So it says weight that is needed to balance a letter. So I'm just going to use W for weight. So the weight that's needed to balance a lever varies inversely. So that tells us when the K is going to show up. So it's going to equals K. It varies inversely with the distance to the fulcrum. So D for distance. So K over D. I could have also set it up initially as WD, weight times distance, equals K. If you are using X and Y to label for the variables, make sure you label what represents what so you don't get confused when you plug stuff in. Though inverse variation is kind of forgiving on that. Now, in order to find the value for K, I need my completed set of information. The information about Willis is asking where should Willis sit, who weighs 150 pounds. I don't have both the distance and the weight for Willis because it's asking me where should he sit. So we don't know both things for Willis, so that's not the completed set of information. On the other hand, Frankie weighs 120 pounds and is sitting 6 feet from the fulcrum. So this is the completed set. We have both the weight and we have the distance. So I'm going to plug those in for W and D. So 120 is the weight, K is unknown, and the distance is 6. Then to solve for K, we'll multiply it by 6 on both sides, giving us K is 720. Now this means that we can use the equation, oops, wrong line. We can use the equation W equals 720 over D multiple times for this situation in regards to balancing out Frankie. We can also use the equation WD equals 720 in the same way. Okay, and then the third phase of the problem is to actually answer the question. We're supposed to figure out where Willis should sit. So I'm going to go ahead and use the same version of the formula that I've been using. So W equals 720 over distance. I'm choosing to use this version just because it's a little harder to use when we're solving for the distance. So what I'll do, since Willis, we know it weighs 150 pounds, we'll replace his weight with 150 equals, and that kind of looks like 160. There we go. Equals 720 over the distance. Now, oftentimes when people are trying to solve this, they make mistakes in a number of ways. Distance is on the bottom, so we can't just multiply by 720 to get distance by itself. In order to solve for distance, we first need to get it out of the bottom of the fraction. There's several ways to do it. The easiest way for most people is just to simply cross multiply. So D times 150 is 150 distance equals 1 times 720 is 720. And then we can actually solve for D, since it's now in the top part of the fraction. We'll divide both sides by 150. This is not going to be a whole number, but that's fine. D will equal 4.8 feet. Or if I turn 0.8 into inches, it would be distance equals 4 feet and 9.6 inches if you want it in inches. Feet in inches. But either way, it's fine. Okay, in this example, we're going to be looking at the function f of x equals 1 over x. And This right here is really just a comma. It might look kind of like a blurry exponent, depending on how closely you can see it. But we're going to complete the table below and use it to graph and look at the graph of the function of 1 over x. This is referred to as the reciprocal function because 1 over x is a way of denoting reciprocals. In other words, flipping the fraction. So if I go to plug in my first x value, replacing x with -3 there in my table, I'm going to have 1 over -3, which we really can't do with anything with, and I'll leave it as 1 over -3. I'm going to go ahead and plot that point. -3 and -1/3 is maybe something like right there. If I do the same thing with f of -2, I'll have 1 over -2, which again we can't do anything with. So we have -1/2. Plot my point. This one's going to be a little bit lower than the last. Then we have -1, so f of -1. And we'll have 1 over -1, which is just -1. Now if I continue, f of -1/2 would start off as 1 over 2, negative though. And when you divide by a fraction, you do keep change flip, so you'll multiply by the reciprocal. So 1 times the reciprocal of -1/2 is -2 over 1. In other words, it's just -2. And I can continue this same strategy. If I plug in -1/3, I'm going to find the reciprocal, which is -3. I'm going to stop there with the first half, and then I'm going to finish the other half. So I'm going to skip 0 for just a second here. If I try to plug in 1/3, it's going to be the reciprocal, which is 3. Plug in 1/2, it will be the reciprocal of 2. Plug in 1, we have 1. Plug in 2, we're going to have 1/2. And plug in 3, we have 1/3. So just quickly filling in the rest of them. Now that I have my table filled out, except for 0, which I'm going to come back for, I'm going to go ahead and plot my other points I kind of skipped over whenever I was just quickly going through with the reciprocals after the first couple. So we have -1/2 and -2, so something about right there. And then -1/2 and -3, or sorry, -1/3 and -3. Then we have 1/3 and +3, 1/2 and 2, 1 and 1. We have 2 and 1/2, and we have 3 and 1/3. So you can see that we kind of have that same shape going on here and here. Now if I go back and actually try to plug in 0, f of 0, 1 over 0, but we can't divide by 0. We can't have 0 in the bottom of the fraction. So it's undefined. Now what this interprets as the graph is there is what we refer to as an asymptote vertically right here, which is a line that the graph approaches but can never actually reach. So as we go closer and closer to infinity, it will get closer and closer to this line. So as we go down towards -infinity on the y-axis here, this line is going to get closer and closer and closer and closer and closer and closer to that vertical asymptote. But it's never actually going to reach the x value of 0. And similarly, on the other side, it's going to be really close to the y-axis, but it's not actually going to be touching it, and then it's going to curve away. You also see kind of the same shape that's happening here. So it's actually going to hug horizontally the x-axis and never actually reach the x-axis due to another horizontal asymptote that runs along the x-axis. Because this fraction, 1 over x, can never take on the value of 0. It can get close to it, like if we keep adding larger and larger numbers, like 500, if we do f of 500, we're going to be even closer. We're going to be at 1 over 500. but it's still not quite 0. And no matter what number we plug in, we're not going to get quite to 0. So we're going to have a horizontal asymptote running from side to side as well. And asymptotes are just represented by dotted lines. And again, they're what the graph is approaching as the graph is moving towards positive or negative infinity, but will never actually reach that value. So just clarifying asymptotes. So an asymptote, again, is what a curve approaches as it heads towards infinity. Now, what that means is it could be, if that's my horizontal asymptote, it could be that the graph is going like this, and we're talking about as x approaches infinity, the asymptote is, or the curve is getting closer and closer to the asymptote. However, we also have situations like this where it's approaching an asymptote, but it may be as y is moving towards infinity rather than x. So as one of the variables is approaching either positive or negative infinity, that graph is moving in that direction, getting closer and closer to a specific line, but it's never actually reaching that line or a specific value. So the reciprocal function is the function that we just looked at. It's one of the parent functions, one of the basic parent functions that you examine. The reciprocal function, some key features about it is that it does go through some of the same points that we've seen other parent functions go through, 1, 1, and -1, -1. Unlike most of the other parent functions, it doesn't go through 0, 0. A lot of the ones we've looked at throughout Algebra 2 have gone through 0, 0. This one does not. Instead, we have two asymptotes that run through 0, 0. We have the asymptote y equals 0, and we also have the asymptote x equals 0, which is the vertical asymptote. And then the shape of the graph, it hugs those two asymptotes and then curves through those points. So we use this information, or we can use this information to help us when we're graphing transformations. And because of the asymptotes, it also takes in, affects the domain and range of the function. So the domain is all real numbers except for where the asymptotes are, and same thing for the range. Okay, so in this example, we are going to be looking at stating the asymptotes and the domain and range for this function, and then we're also going to be graphing it. This function is a reciprocal function, just has some transformations going on. We can tell it's a reciprocal function because it has x just occurring in the bottom of a fraction in just one time without any exponents. So as far as transformations go, I'm going to use the same rules as I have used in the past. The stuff inside with the x will occur in the bottom. Then the stuff outside would be over here. Up here would be considered connected by multiplication. And anything out front would also be multiplication. And this would all be outside stuff. I shouldn't put just multiplication out in front because depending on how the equation is written, it may not actually be multiplication. But the stuff on top is implied to be multiplication, and the stuff off to the sides is also implied to be outside. So same rules as before though. If it's outside, it affects the y values and in the same way. So I have a -2 on top and a +1 off to the side. So we're going to have y times -2 and +1. And the fact that this is affecting y is just because of how you can rewrite fractions with multiplication. We can rewrite this as -2 times 1 over x minus 2 plus 1. So this is affecting outside and not down with the x. Therefore, it's affecting the y values. Then inside stuff, so inside the bottom of the fraction with the x, is just the x minus 2. And inside affects the x values in the opposite way. So what we're really going to do to our x values is we're going to add 2. Now I'm going to start with the asymptotes here. So my asymptotes, they are normally at x equals 0 and y equals 0. Those are my normal asymptotes. However, we have transformations going on, so I'm just going to apply my transformations. My rule for x is to take x and add 2, so our new asymptote is going to be x equals 2. And my rule for y is to take my y values, multiply by negative 2, and then add 1. So 0 times negative 2 is still 0, and then plus 1 is 1. So those are my asymptotes. Once you know the asymptotes, domain and range are pretty easy to do. So domain is all real numbers, except for where you have an asymptote. So our asymptote on the x is x equals 2, which means our domain is all real numbers, except for when x is 2. And similarly, range is going to be all the y values, so all real numbers, except for where y has an asymptote, or except for where our asymptote is. So y just can't be 1. So there's domain and range. Okay, now we just need to graph this. Now to graph it, we have our x asymptote at x equals 2. Now because it's an x asymptote, that is actually a vertical line. It's a vertical line because it's a vertical line where all the x values are 2. Here's where x is 2. Along this line, all x values are 2. Okay, and for our other asymptote, the y equal to asymptote, this will be a horizontal line where all the y values are 1. Here's where our y value is 1, and every spot on this horizontal line, this horizontal asymptote, would have a y value of 1. Now, it helps to have some extra points to figure out the exact shape, and as we saw earlier, the graph of the parent function goes to the point 1, 1, and negative 1, negative 1. I know because of my transformations, these are going to turn into, well, we're going to be adding 2 to x, meaning it's going to be 3 and positive 1. And then for y, we're going to multiply by negative 2 and add 1. So 1 times negative 2 is negative 2, plus 1 is negative 1. Then negative 1 times negative 2 is positive 2, plus 1 is 3. So we have 2 other points to graph. We got 3, negative 1. 3, negative 1. There we go. And 1, 3. And then to graph it, we hug the asymptote, curve up through the point, and hug the asymptote. Then we hug the asymptote, curve out through the point, and hug the asymptote. Some tips when graphing, since I do know I multiplied by a negative, normally this point is normally up here, is normally above the asymptote, and this one is normally below the asymptote. Because we had that reflection, it flipped. For the reciprocal function, they're always across from each other, so whether one is here and the other is here, or one is in this section between the asymptotes and the other one is in this section. Because my dilation was multiplying by 2, I know instead of being 1 away from the asymptote, now it's 2 away from the asymptote. So both pieces, that 1 point is 2 away from the asymptote. They are 1 unit away from the vertical asymptote, though, because we did not have any horizontal dilations. So